All right, so welcome everyone to the SPACE webinar series, and I believe this is our third webinar for this for this year 2021, and we are very happy to have Gordon Wetzstein today with us to give a wonderful talk on neural imaging and signal processing, and in the context of computational imaging, computational photography. Here's a brief bio of Gordon. He's an assistant professor of electrical engineering and by courtesy computer science at Stanford University, and he's a leader of the Stanford Computational Imaging Lab and a faculty co-director of the Stanford Center of Image Systems Engineering. And he works at the intersection of computer graphics, computer vision, computational optics, and applied vision science. And his research has a wide range of applications in next generation imaging, display, variable computing, and microscopy. And prior to joining Stanford, he was a research scientist in the camera culture group at MIT, and he received a PhD in computer science from the University of British Columbia in 2011. And he has received numerous awards, including an NSF Career and Alfred Sloan Fellowship, an ACM SIGGRAPH Significant New Researcher Award, a Presidential Early Career Award for Scientist P. Case, SPIE Early Career Achievement Award, etc. And so for today, we'll be hearing about his recent works in the domain of computational imaging and with especially with machine learning. And so I very much look forward to the talk, and let me hand over the mic to Gordon.
Well, great. Thank you so much for having me. And good morning from California to all of you, even though it may not be morning where you are right now. It's a pleasure to be here, part of this talk. And I'd like to give you a little bit of an overview of some of the topics we've been working on recently. And with we, I mean, myself and my team here of a couple of PhD students and postdocs at Stanford. And we work at this intersection of imaging and displays, but driven by advanced computation. And more recently, obviously, AI is a methodology of choice for many of these algorithms. And what I'll try to do with my talk is, talk about a couple of different topics at a somewhat high level and try to convince you that AI can be a really meaningful tool to enable new capabilities for these imaging and display systems. Let me just start with a little bit of a historical slide. I kind of like to draw the connection to the history here. Many of you have probably seen these photographs that you can see on the left. These were captured by a fellow named Edward Muybridge back in 1878 or so. He was commissioned by Leland Stanford, who was the governor of California at the time, because apparently he had a bet with some of his friends on whether there was ever any time where the horse had all four hooves up in the air. For some reason that wasn't known at the time. So Edward Muybridge set out to go to Stanford campus, which was a horse breeding farm and not a university at the time. And he set up this experimental photography system that you can see on the right, where he used tripwires spun across the track, and the horse would run, trip the wires, and each of these wires was connected to a mechanical shutter in front of a camera to trigger the exposure time of a photograph. And what you get is a stop motion sequence that you basically can see on the left. And he was able to prove that Stanford was right. And there's a point in time where the horse has all these four hooves up in the air. So the point is that research on experimental imaging systems, and in this case, a high-speed imaging system, have been part of the history at Stanford since before it was a university. And we carry on this tradition with modern incarnations using computing, machine intelligence, and other modern systems. So my group is maybe a little bit special in the world of computational imaging because we do work on a couple of different topics, which include computational cameras. How do you design new types of cameras and algorithms? But we actually work quite a bit on computational displays, for example, in applications to wearable computing or VR, AR. But we also work on, end-to-end optimized optical systems, single-photon imaging, and a few other things. And I don't have time to go through all of these today, but I want to give you a little bit of a glimpse of some of the things that we've been working on recently. So the first topic I'd like to discuss briefly is this idea of computational imaging with individual photons. And to start out, I want to give you like a bit of a motivating example of a scene that looks really boring. This is an optical fiber, and we use a pulse laser that we couple to this optical fiber on the left. So you can see that basically the photons scatter through the fiber, and some of the photons will scatter out of the fiber towards the camera. So if you take a regular image of this fiber, it looks like kind of like this. You know, the pulses will kind of attenuate as the light propagates through the fiber, and you know, it looks a little bit boring. But if we leverage emerging single photon sensitive detectors that have picosecond accurate timestamping capabilities, we can visualize what we call a transient image, which is basically visualizing light in flight. So we can see individual pulses of the laser being shot into the fiber. And because our imaging system is fast, it's basically faster than the speed of light to some extent, it has picosecond accuracy to be precise, we can resolve at centimeter resolution how light propagates through air or through some medium like this fiber. And what we see is that these pulses are shot millions of times per second into the fiber, so we can dramatically slow down this propagation. We can see how the pulses will broaden as they propagate through the fiber because of the scattering inside the fiber. At some stage, they're going to scatter out, the light's scattering out on the lower right, and we can see this periodic process happening. So this is really cool. It's maybe not all that useful, but we can actually visualize how light propagates in space. And this is enabled by an emerging technology known as single-photon avalanche diodes. So this is a new type of technology where we have an avalanche photon diode that is biased above the breakdown threshold for the voltage, and it basically creates these electron avalanches. And what that means is that you can couple it with a picosecond laser that shoots light into a scene. Some of this light will be directly reflected back to the detector. So we call this the direct reflections. But some of the light will actually bounce around in the scene through interreflections or other global illumination effects, maybe scattering. And it will arrive a little bit later at the SPAD. And the SPAD has, some probability to detect any one event in this returning pulse that includes the direct and the indirect reflections. It has to repeat this process over and over again because, again, it can only detect one photon event per pulse, and then it has to be reset. So you have to do this millions of times per second, and every time you do that, we don't count the number of photons like in a conventional camera or charges. We timestamp this photon event using a time-to-digital converter that has some bit precision for this timing, okay? And so if you have a single detector or multiple detectors in an array, then basically each one of them measure histograms of photon counts, where the histogram axis is basically time. So you count the number of photons that arrived within a certain time bucket. And each detector will record this temporal histogram. So for a 1D array, you will get a 2D image because it has one spatial dimension, one temporal dimension. For 2D array, you're going to get a 3D volume that has X and Y sampling positions and the time. And so we don't really fabricate these devices. We have, built experimental systems around them. And our focus is mainly on the signal processing optimization, for example, to recover these transient images from very noisy raw sensor data that has temporal blur, that has very few photon counts, that has lots of background. So these are the kinds of inverse problems we solve. And you've probably seen a few people in the seminar series talking about how to solve inverse problems in detail. So I don't want to go too much in depth here, but that's kind of our bread and butter. Now, for useful applications, I said this was educational, but maybe not all that useful. Well, it is actually useful. SPAD detectors combined with picosecond lasers and some kind of a scanning system, either, for example, using a Galvo system or like a MEMS-based scanner or something else, is used for LiDAR, specifically single photon LiDAR. This is a next generation LiDAR platform where we shoot pulses into the scene. We measure the time of flight of the light that is returning back to the detector, we scan this point over the scene and thereby record a 3D point cloud of the world in front of us or in front of the detector. For high power systems that typically operate in the infrared regime, this enables long range single photon LiDAR systems that are critical for emerging autonomous driving systems. And we see these systems becoming more and more practical, the cost being reduced, and this is really driving a lot of these self-driving cars that you can see driving around already here for a few years now, but that probably soon will conquer the world. More recently, specifically last year, Apple also introduced with their iPad Pro 2020 a mini LiDAR system in their consumer grade products. And that's also built on a SPAT. There's a single diffuse SPAT in there with a MEMS scanned pulse laser that captures a 3D point cloud around it in order to give you a depth map of the scene around you, which is helpful for applications such as augmented reality or measuring your home for virtual furniture trials and things like that. So these systems are already in your pocket. They're becoming smaller, cheaper, and better. And what we do again is to maybe think about what some of the capabilities are that are enabled by this extreme timing precision and photon sensitivity beyond just direct imaging. So one idea that came to mind was this idea of whether you can see around a corner. So if you have an occluder between the object that you want to see and the imaging system, well, conventional wisdom says you can't image it because the light doesn't go through the occluder. But leveraging these indirect reflections, the indirectly reflected light, we may be able to develop algorithms that can actually resolve the hidden shape of these objects. In particular, here's a little video that animates how that may work. In this case, we shoot a laser pulse from our imaging system. Some of the light directly reflects back to the detector from a visible wall, but some of the light actually scatters off of the visible wall into the hidden part of the scene, interacts with the object there, then gets scattered back into the line of sight, and then gets back all the way to the camera. So we're talking about a third bounce light here. It bounced off of the visible wall, then off the hidden surface, then back to the visible wall, and then all the way back to the camera. So these photons bounced precisely 3 times. And they have a different time of flight. So in this example here, we detect the first bounce of the directly reflected light, maybe after 2.7 nanoseconds, which corresponds to about 40 centimeters. And then we measured a third bounce that is about 24 centimeters away from that visible wall. So we don't directly measure the geometry of this object because there's a lot of ambiguity in where it could have come from. It could have come from anywhere on this arc because that arc, all points on this arc basically have the same time of flight. But by measuring multiple points on the visible wall and developing clever algorithms, we're actually able to recover the 3D shape. So specifically, we're going to use this system to capture a 2D array of sampling points on our visible wall, which for simplicity in this case is just a flat white wall. And so that gives us a 3D data cube that you can see on the upper left. I mentioned this earlier. This 3D data cube contains XY sampling positions on the wall. But for each sampling position, we capture a histogram with the time of flight, where we count the number of photons that arrived within a certain time bucket. And you can see that in the upper left. We digitally remove the direct reflections because they don't tell us anything about the hidden object. So we're really left with a transient image of the light transport, of the indirect light transport, the time-resolved indirect light transport of the hidden scene. And it looks like a bunch of blobs. There isn't much that you can see. So here's the transient image visualized in 3D and played back over time for a mannequin that we captured with our experimental imaging system. And then what we've been focusing on is developing robust and efficient algorithms to process data like this to recover the 3D shape. And one of these algorithms that we developed, we called the light cone transform. That was a closed form solution for the large scale inverse problem to process this this time-resolved indirect light transport, and directly using this transform, and which enables efficient inverse filtering methods to process this data. It was built on a geometric optics model of the light transport, so it makes many assumptions that may not hold in the real world. But the initial results that we got in our Nature 2018 paper were very, very exciting to us. Spent a lot of time, about a year, to continue to develop our hardware system, and my student David Lindell spent a lot of his time doing that. So here's the upgraded hardware system on a card. It includes a single SPAD, a pretty big laser, timing electronics, galvo system, and so on. And in this case, we took it outside and captured some hidden scenes behind an occluder outside in indirect sunlight. You can see on the right that the imaging system really can't see what's behind the black curtain. It's only scanning the wall over and over again. And at every point where it scans, it basically records a histogram of the time of arrival of these photon events. And on the left, you can actually see the indirect reflections on the statue, on the plant, and so on. These are all indirect reflections here. And these are exactly the types of photons we're looking for that tell us something about the hidden scene. So here we're cheating a little bit, and we take a camera and put it behind the occluder, so that visualizes the indirect reflections a little bit more. Here, for example, in the armpit, on the statue, or on the table, in the plant, we can see the indirectly reflected light. And again, that's exactly what we're looking for, the time-resolved indirect light transport that makes it all the way back to the wall and then back to the detector. So there are really only a handful of photons coming back every time you shoot a laser pulse, maybe just a few, because you may be familiar with this 1/distance square fall off of light when you record directly reflected photons. Well, in this case, we have 1/R6. So there's orders of magnitude more light loss because the light scatters from diffuse surfaces multiple times along its path. And every time the photons scatter in all directions isotropically, but we're only actually capturing one of the returning paths back. So this is extremely challenging. Here are some experimental measurements for this outdoor experiment, which are really stunning. And we see two things. Well, first of all, we see the wall and a bunch of noise. So this is inevitable because we get ambient photons coming in from the indirect sunlight. And we don't do anything special to process the wall or the varying reflectance on the wall. But what's more interesting is we see these ripples that look like wave patterns on a pond. And these are literally the time-resolved indirect light transport effects that we're looking for. These are actually three-dimensional intersections of four-dimensional hypercones that describe the propagation of light in free space. Okay, so these are our measurements, and again, we process them to basically get a 3D reconstruction of the scene. In this case, we can see the reconstructed 3D data cube that shows the statue pretty clearly. It shows the pot of the plant. We don't really see the plant. We see the white tablecloth. We don't see the black tablecloth. So clearly there's a problem with, imaging very dark objects because they simply just don't scatter enough photons back for us to see them. But the brighter parts of the scene, we can clearly make out. We get a 3D picture of them with a resolution of about 512 by 512 pixels in this data cube. So I haven't really told you about, again, how we actually compute this. I just want to hint a little bit at the solution, or one of the solutions that we worked on in our SIGGRAPH 2019 paper. There we built on the wave equation that you may be familiar with. So this is a time-dependent wave equation that relates the spatial derivatives of the wave field to the temporal derivatives. And this is a four-dimensional equation that includes three spatial dimensions and one temporal dimension. And what we realized is that with our confocal scanning method, so basically our point scanning method on the wall, we're actually measuring a boundary condition of this wave equation, specifically the boundary condition where we have spatial information on X and Y, which are the planar locations on the wall for Z equals 0. So we want this third dimension that's missing, the Z dimension, but we have a different dimension. We have this time dimension. So this is a 3D boundary condition of this four-dimensional equation. And what we now can do in this specific case of a confocal scanning system is we can migrate this boundary condition that we measured to the other boundary condition that we actually want, which is the boundary condition where the field is given at x, y, and z for all hidden dimensions, but at time equals 0. And again, this is unique to this confocal scanning system because this boundary condition of the field at time equals 0 is equivalent to the surfaces in the hidden part of the scene, all emitting a spherical wave, and it just comes out of the math. So we built on fast range migration techniques developed in the seismic imaging community back in the 70s or so, and enabled real-time reconstructions of these 3D hidden scenes. That's kind of how it works in a nutshell. More recently, we've been looking at slightly more challenging inverse problems in this space. So this problem of looking around a corner or looking at the light scattered off of a diffusely reflecting wall is mathematically actually equivalent to seeing through a thin diffuser. So a thin diffuser is one where you have a very thin diffusing material that includes exactly one scattering event, and you have an object behind it. So that's the transmissive equivalent. So here we're looking actually at a thick diffuser. So this is a little bit different. And it's actually more challenging because the light that you shoot on it from one side of the scene will actually diffuse through the diffuser as described by the diffusion equation. And then there's some free space propagation to the hidden scene, in this case, the letter S. There's free space propagation back to the thick diffuser. And then there's another diffusion event going through the diffuser before you can actually measure the returning photons. So again, building on similar concepts as what I showed you before, but with the addition of considering this diffusion through the thick diffuser, which basically ends up being a 3D deconvolution, we were able to process time-resolved indirectly scattered photons that you can see here on the left. You really can't make out much anymore. Like these nice ripples on the pond, they're actually gone because everything's diffused together. It's like a low-pass filter if you want. And with conventional techniques like time gating, you really can't see much in this data. So building on these inverse methods that we've been looking at for processing time-resolved indirect light transport, we're able to better reconstruct 3D objects behind the diffuser, in this case, the letter U and T, where we don't know the shape, we don't have access to the other side of the diffuser, and yet we can recover their shape approximately. So this is really exciting. People will probably immediately think about medical applications. Well, one caveat here is that the timing resolution is, as I was saying, a few tenths of picoseconds. So that gives us centimeter scale resolution. So if you want to look through tissue, this currently is not quite applicable to this. You can think about this as maybe a large scale version of techniques that are known maybe from OCT or other medical imaging techniques, but more applicable to larger scale things. Okay, so this is like a super quick overview and high level overview of some of our work on single photon imaging, and there's lots more work in progress, and you can find a lot on our website too if you're interested in this topic. Next, I'd like to just tell you about an idea that I found very compelling. I've been working on in this field of computer vision for a long time, and over the last maybe 8 years or so, the paradigm of how we do computer vision has shifted towards machine learning and AI. And the basic idea in computer vision is that instead of writing an algorithm, we train an algorithm in the form of a neural network, and we do that by building some neural network architecture using a large training data set of example images, and send it in the training time, sending that through our neural network, compare the result with the loss function to the ground truth, and backpropagating the error back into the parameters of the neural network, the weights and the bias values. And so if we do this over and over again, hopefully we'll be able to train a network that excels at some task. So this is kind of how we develop and design algorithms these days. Well, one idea that we started working on early in maybe 2017, early 2018, was to extend this concept to hardware as well. So can you use the same techniques to jointly optimize optics or other physical parameters of a camera, for example, together with the image processing algorithm end to end? And the answer is yes. The question is, why is this why may this be useful? Well, consider a domain-specific camera that is really optimized for one specific task. For example, you want to build a camera and its only purpose in life is to classify cats, for example. Then the question is, well, is there maybe a better lens or some better capture setup, exposure times, a better sensor, some other better hardware configuration that excels at this task, maybe at the cost of not doing as well at other tasks? And so we set out to try to answer this question. And the methodology here is that you basically think about your physical system and your digital system as a single system. There are multiple different interpretations that I'll talk about in a second, but the physics and the digital systems are trained end-to-end in simulation using some data set. And the physical layer in this case requires you to have a differentiable simulator for what happens in the physical part. You train it end-to-end in simulation. Then during inference, you can fabricate or fix the hardware, for example, by fabricating the lens and putting it back into the hardware system. There's maybe some refinement that you can do on the digital layer after you fabricated it because of fabrication tolerances. Maybe the physics don't do exactly what you predicted them to do, but you can refine the network after the fact. And this, you can think about this idea in two ways, or I think about it in two ways. One interpretation is this idea of thinking about this as an encoder-decoder system. This is a classical concept in AI, where in this case, our physical layer, the optics, are basically the optical encoder, and the neural network is the electronic decoder. So what the encoder does is it projects the plenoptic function or the rich visual information of the world onto the sensor, which becomes the bottleneck. And the sensor integrates over the dimensions of the plenoptic functions, including its spectrum, depth information, polarization, and a lot of the rich visual information that is included in this plenoptic function is actually integrated out on the sensor and then recovered by this digital layer. If you want to do things like high dynamic range imaging, depth imaging, or recover other aspects of the plenoptic function. The other way of thinking about this is to think about it as a single neural network, a hybrid optical-electronic neural network that simply executes some of its parts in physics and some of its parts digitally in the computer. And I'll show you two or three example projects where we leverage different interpretations. So as I was saying, like, we've been working on this topic for quite a while, probably introduced it back in early 2018 with our paper on end-to-end optimization of optics and image processing at SIGGRAPH. But then, we set out on a journey to kind of explore what the killer app for this idea may be. And we looked at many different things, including, trying to implement convolutional neural networks in optics, doing depth estimation and object detection, trying to improve those, thinking about shrinking the device form factors of cameras, making them smaller and thinner, using thin diffractive optical elements where we can correct the image quality in post-processing, high dynamic range imaging. We've looked at, different optical designs that make the computation more efficient. I just want to draw your attention maybe to one or two of these projects. So one was called Neural Sensors, and we published this at ICCP last year. And the idea there was to do something that's known as video compressive sensing. So the idea is that, you use a camera. In this case, my postdoc Julian is really a wizard with programmable cameras. He has this sensor that he can fully program. Every pixel can be programmed with a different shutter speed, and it can basically, every pixel can record a different coded exposure throughout some shutter time. And what he was able to do is train a network that reconstructs from a single coded measurement like this. This is a single image, reconstruct a full video with about 32 frames or so. And we trained that end to end with the per pixel coded shutter time, so that the picture that you record looks kind of like this. It looks a little bit funky. Basically, again, like the exposure times are different, and they turn on and off throughout the exposure time in pre-optimized patterns, so that the network that Julian was developing was then able to recover the full balloon popping from a single coded measurement. So if you're interested in this topic more, I refer you to our ICCP 2020 paper. The other idea is this interpretation of thinking about it as an optical neural network. And my student Julie was working on this to try to optimize something that would implement a CNN, or at least a single layer of a CNN in optics. And the way we think about this is, again, that we jointly optimize a phase-coded aperture inside a camera together with a neural network that processes some of this data, in this case for the task of image classification. And our system implements this on a benchtop where we have a small display, like a digital micromirror display, where we can show arbitrary images. We have a 4F system. And then in the center here, there's a face mask that is pre-optimized, static, that doesn't require any power, and that optically processes this image in a Fourier optics setup. And then there's a sensor here recording the image. And again, using our end-to-end optimization, we were able to optimize the diffractive pattern of a diffractive optical element that kind of looks like this under white light. Kind of looks somewhat random. And what you see is there's a couple of different grading type patterns, but the optimized codes, optical codes, are actually included in this. And if you drop this in the aperture plane of this imaging system, what happens is this: you show an image on the DMD that you can see on the left, unmodified. This is from the CFAR10 data set. So this is a set of low resolution images that's typically used for image classification. And what happens in optics is that this specific diffractive optical element that I showed you actually creates multiple copies of the input image, in this case, 4x4 copies, 16 copies. And each of these copies is a variant of this image blurred with a different blur kernel, with a different optical blur kernel. So this is a different convolution. This is basically implementing a convolution with a pre-optimized blur kernel. And specifically, we have, in this case, 8 different blur kernels. These different sets of copies actually correspond to the positive and negative numbers of the corresponding blur kernel. And in this way, we can actually implement a single layer of a CNN in optics. We have a second fully connected network in electronics that does the image classification. And we were able to show that we don't lose much classification accuracy for this hybrid optical-electronic CNN compared to a 2-layer fully digital CNN. And what that means is you can bring down the latency, because whatever happens in optics happens at the speed of light. You get twice the classification accuracy for the same power that you run your single-layer digital network at, or half the power for the same classification accuracy. So we believe this can be useful for systems where size, weight, and power is a problem, such as in drones, or where latency is a big issue, for example, on autonomous systems. But this is more of a toy example that hints at the capabilities of a system like this. I just want to say that it's tough to implement optical nonlinearities at low power. So we were not able to do that, which is why we constrained this to a single layer of a CNN. But other people have worked on optical nonlinearities that typically work at high power. And I published a recent review paper in Nature on AI and the use for AI in optics and optical computing that just came out maybe 2 months ago. So if you're interested in this topic, I'll refer you to this article. Here's a quick teaser of some of the more recent work that we've been looking at. There was a talk, I think the first talk in the series from Raja was actually on, end-to-end optimization of optics and image processing for depth estimation. So this is something that we've worked on quite a bit too. And we have a paper coming up at ICCP this year where we show that, again, with a pretty small network that's very efficient, if you just take a conventional image, these are captured images, run a monocular depth estimator on it, the depth estimation accuracy isn't very good if you use small networks. I mean, this may be different for very specialized, large-scale neural networks that do monocular depth estimation. But for small-scale networks, they're not very good at monocular depth estimation. But when we apply this idea of end-to-end optimization of optics and image processing, drop a phase-coded mask into the aperture of a camera, we can record images that are kind of always blurry, so they don't look very good. But from these individual images, we can now estimate the all-in-focus images and the depth maps simultaneously using our pre-trained neural network, and thereby recover much more robust depth maps of fine details like these plants. and the RGB images simultaneously. So again, if you're interested in this topic, this paper should come out in a couple of weeks, and I'll refer you to that. Okay, so these were two examples where we can combine, advanced computing with AI or using AI with optical designs for two different applications and enable new types of imaging modalities. I want to talk a little bit about displays too, because the same idea of co-designing optics and computation also enables new types of user experiences, especially in AR and VR. And AR, VR, as you know today, I mean, the fundamental principle of operation is kind of the same as what Charles Wetzstein envisioned with his invention of the stereoscope back in 1838, where you just see two different images, one with each eye. And it turns out that the National Academy of Engineering in the US has declared enhancing virtual reality as one of the grand challenges of engineering of the 21st century. So there's a lot of activity in designing the light engines, the optics, the displays, and other aspects of networking capabilities, rendering, computer vision, HCI. These are complex systems that require lots of different engineering. So great for the IEEE community to jump on one of these topics. We work on one of those topics, and that is computational displays. And there's a couple of challenges with existing displays in this space. In particular, this challenge that you're typically using a magnifier principle to generate the images that you're looking at. So what that means is you have a micro display like your phone inside the head mount. You use a magnifying lens to create a virtual image that is basically a magnified version of that image. And that's what you're seeing. So each eye will basically see a 2D plane floating in space in front of that eye at a fixed distance that is governed by the Gaussian thin lens equation. And this fixed focal plane design is actually not natural. In the real world, objects live in a three-dimensional world around us, and our eyes will naturally focus or accommodate to multiple different distances. So pretty much all existing VR and AR displays do not present focus cues. They don't allow for these focus cues because they show you a 2D plane floating in space. And that causes divergence accommodation conflict, which creates eye strain, potentially nausea and other adverse effects. So my group has been working on this problem for a few years now, and we've been developing different types of technologies to address this. One type of technology that we looked at was gaze contingent varifocal displays. So these use eye tracking and either focus tunable lenses or some kind of mechanical actuation to drive the focal plane of the display to the area that you focus, fixate with your fovea. And so this idea was also picked up by Facebook or Oculus later on, and some of their recent prototypes use exactly this technique. We looked at near-eye light field displays that try to project a 4D light field with spatial and angular diversity of the rays into your eye so that you don't need eye tracking and you can just freely focus. This idea was kind of partly implemented in the Magic Leap ML1 prototype. And then more recently, we've been looking at holographic near-eye displays where computing is a key part of the image formation model. And these use coherent light typically. And I just want to give you a quick sense of how AI and algorithms can help make better holographic images. So a holographic near-eye display in principle is pretty simple. You have a laser or some kind of a coherent light source. It emits a wave. You have some optics that may collimate this wave. The resulting plane wave is incident on a phase-only spatial light modulator, or SLM, and this SLM can delay the phase of the light in a per pixel manner. So the resulting deformed wavefront continues to propagate in free space, and through interference, it creates an image that you can observe through an eyepiece. So you still need a magnifying lens because the image is going to be very small. But this is perfect for AR and VR applications, which exactly work like that. Now, the challenge is to calculate a phase pattern that you can display on the SLM that then creates the target image that you'd like. And in theory, this sounds simple because you run your favorite phase retrieval algorithm, maybe. But in practice, it's a little bit harder because typically the simulated model that you have for this free space propagation doesn't match exactly what happens in the physical setup. There are small amounts of optical aberrations, nonlinearities in the phase, and other slight variations in what happens between the physics and the simulation, and that typically results in very low image quality. So we came up with a really clever way to use a camera in the loop to actually capture the images that are resulting from the physical setup, then taking the captured image and comparing it with the target image that you want to see. The problem is then, okay, you don't have an easy way to backpropagate the error back into the phase pattern. Otherwise, you could just implement an optical phase retrieval method. But we came up with a way to approximate the gradients of the forward model, basically simply using the gradients of the simulated model that is imperfect. So you work with imperfect gradients, but it turns out that this actually works really well, and you can develop an iterative phase retrieval method that uses the physical forward image formation that is perfect and doesn't suffer from any approximations, and then only the backward pass, where you use the gradients of this of some other proxy image formation model to propagate the gradients back and do that in an iterative fashion, works really well. So I'll show you what that means on our system. We tested a couple of different computer-generated holography algorithms. For example, some of the state-of-the-art algorithms like Wirtinger Holography. It suffers from lots of artifacts and speckle. It just doesn't look very good. And this is a 2D image. And it's only constrained within the white box. So outside that box, the light is unconstrained. So this is kind of what we were able to achieve with our camera in the loop optimization technique. We can even play that as a video. So, it's still not perfect, but in terms of image quality, this is probably the highest quality, full color, 1080p hologram that anybody has shown to date. And we published this early last year at the SIGGRAPH conference and showed some demos there. And then the full technical paper came out at SIGGRAPH Asia last year. So we call this neural holography, and we can even do this in real time. If you're interested in this general topic, I'd recommend taking a look at the course notes and lecture material for my course on virtual reality, EE267, that I teach at Stanford, where we built a head-mounted display from scratch with the students. So this photo is from happier days before the pandemic, when we were still working in the lab. Okay, so we have a couple minutes left, so I want to end the talk with a few fundamental questions on not just computational imaging, but signal processing and signal representation in general. And the question is, how should we represent signals? It's something that you don't really think about much because, there are common techniques. Digital images we represent as pixels, 3D shapes we represent as either discrete meshes or point clouds. Audio signals we represent as discrete samples. So this idea of discrete signal and image processing has become so ubiquitous that we don't even think about whether this is the best way of doing it. Well, very recently, people in the world of 3D computer vision have actually gone back to the original idea of having continuous representations for some of these signals, in particular 3D shapes. And using neural networks, you can actually easily build a continuous representation of a 3D shape. For example, using a multi-layer perceptron, which is just a fully connected network on the left, that takes as input a continuous XYZ coordinate, and that gives you as output a value that tells you whether you're inside the object or outside the object, or if this location is occupied by an object or not. Or there are a couple of different ways of doing this, but it's a continuous representation that is enabled by neural network representations. Now, the problem is that it turns out that these multi-layer perceptron architectures using ReLU activation functions are not very expressive. They don't have very high capacity. So if you try to represent a more complicated shape like a room, the network itself doesn't have enough capacity to actually represent that, and you get poor looking results. So last year we worked on, and this is true for representing images, shapes, audio, if you maybe want to do a wave field or something like that. We worked on a concept that we called sinusoidal representation functions, where we used periodic activation functions in small scale multi-layer perceptrons. It turns out that these nonlinear periodic representations are excellent at overfitting images, 3D shapes, audio signals, and even quantities like wave fields. The cool thing about this is that we can now not only represent a signal in that way, we can also do computation with them. As you know, the sign is infinitely differentiable. So it turns out that without any formal proof, that the derivatives of our network representation actually closely resemble the derivatives of the target signal. So when we try to solve something like a Poisson equation, where we supervise the gradients of our network representation by the gradients of a target signal, which you can see here. So we just give it the gradients of a target image, use different neural network architectures to try to fit those gradients. And turns out that only our siren representation, even compared to all these other representations, is able to fit this image well automatically. We didn't supervise on the image, we only supervised the gradients. So this is really cool because now we can solve differential equations on continuous representations that don't need a grid. We can basically get rid of the grid, which is the main memory hog for all of this, and use our implicit representation. And solving these types of differential equations is great for representing shapes from range scans, for example. As you can see here on the right, we can represent 3D shapes with a lot higher fidelity than other types of representations. We can represent entire rooms. This is the room I briefly showed you earlier. So on the left is the same network using ReLU activation functions. And on the right, we use our sinusoidal representation function, which is just the sine as a nonlinearity. And again, I'm not claiming that the sine is the new nonlinearity that replaces all computer vision algorithms or all AI algorithms, but it's fantastic at overfitting signals, like these types of signals. And the cool thing about this, and this is just the last slide I'm going to show, is that we can even solve differential equations on this, as I was saying earlier. For example, the Helmholtz equation. So if I give you a initial condition, such as a source in the center of an image, and this is a complex valued field. Again, my signal is represented by this neural network, denoted as phi here, and I apply these conditions that are governed by the Helmholtz equation, which relate the Laplacian of the signal to some other boundary conditions. I can actually solve this complex valued problem very well. Again, this is an initial value problem. We've looked at boundary value problems too, and people have looked at using neural networks to solve differential equations for decades. And I think we've now finally found something that actually works, because previous attempts were mainly limited by the representation power of the network and the ability for these networks to represent gradients and higher order derivatives well. So I think we found something that's really worthwhile looking at. And this kind of concludes my talk. The point I was trying to make was that, using modern AI techniques, we can solve long-standing problems, both in optical imaging, in single-photon imaging, in displays. And if we think about the underlying techniques of how we actually represent these signals, it has a fundamental impact on how we solve these problems and what we can do with them. Apologies. Thanks for your attention. I'd be happy to answer any questions.
Thanks, Gordon. That was very interesting, especially the last part, what you were saying. There are questions in the Q&A, but usually we begin with questions from the panelists. And so I could start off, since I'm the host, and ask a couple of questions, and then we'll see if other panelists get questions from them, and then go to the audience. So I had a couple of questions. The first one is when you were talking about deep optics and you were using simulations to model the physical layer. And so this is kind of, this is, I think, quite important for a lot of the computational imaging applications where we are looking at co-designing the hardware part and then the software part. And the question is whether you said something about retraining the network after the fact if your simulation doesn't match reality.
Yeah.
And so can you say a little bit more about this, because it might be that in applications that reality has aspects, components imposed on the data that have not been modeled by the physical simulations yet. And so when you have discrepancies like that and you're deploying the system in the field, what kind of retraining do you think makes sense?
Yeah, that's an excellent question. So, so again, if you want to train your hardware with an AI algorithm, you just need a simulator for it. And what we typically do is we simulate the depth-dependent point spread functions of the system. So that's the extent to what we do. What that means is you take a point at infinity that becomes a plane wave by the time it hits the lens. We use scalar diffraction theory to model the interaction of this plane wave with the diffractive optical element or the lens, and then propagate it in free space to the sensor. That allows us to, calculate a point spread function, but under certain assumptions, right? The assumptions are that, there's this paraxial assumption, for example, baked into the diffraction-based image formation, the free space propagation, for example. There is you can only evaluate this integral, the diffraction integral, at so many discrete wavelengths. You can only evaluate it at so many different discrete depth layers, for example. So you need to make approximations to make this fast or tractable. And in the physical world, you integrate continuously over the spectrum. Maybe the point spread function has a little bit of spatial variation instead of being completely constant. So maybe it's not a shift invariant system. And there are other approximations that we're doing in our simulation. And simulation always works well, but once you fabricate it, the precision to which you can actually manufacture these optimized optical elements may be limited. What one of my students, Hayato, spent probably the last 2 years in the clean room refining a grayscale lithography technique, like a process to develop free-form diffractive optical elements that we can basically program with our AI algorithms. And every lens that he does, even if he fabricates the same lens over and over again, comes out slightly differently, right? So this is a big challenge. And in order to cope with this, the PSFs that we get look very similar to the ones we optimize, but they're not exactly the same. And so, what we then typically do is do a little bit of a refinement stage where we then capture the PSF, do a parametric fit to that PSF, so that, and then fix that in our end-to-end design so that the optical system is fixed, and we will continue to refine the network in simulation again to try to adjust a little bit better to what we actually see in the physics. And as you said, if the simulated and fabricated PSFs match pretty well, which is hopefully the case, if you have a good simulator, then that may be okay. But if there's quite a bit of discrepancy, then you don't know what you're going to get, right?
Right.
I would say maybe also just to follow up on this, I would say, on this question of where's the killer app for this, I would say it is really something that you should think about as a modern way of doing point spread function engineering. People like W. Murner, Raphael Piestun, and others in the optics world have worked on this PSF engineering, at Dowski also, on this idea of PSF engineering for decades. Now we just have better tools to do this. And we can have the PSF adjust to a high-level task, like a classification loss or something else. And this was inconceivable before. Before we were only able to put metrics like Fisher information or other things on the PSF itself and try to optimize that. Now we can put a high-level loss function that's dictated by a classification loss or a object detection or tracking loss or some other high-level loss, and have that dictate what the best PSF should be. And that's really exciting. That opens a lot of new directions. But again, depending on what loss function you're using, depending on what the end-to-end optimization does, the sensitivity of the physical part can be high or not. It really depends on the application, and it is something that you need to study. So, this is a topic that's been explored by various groups in different contexts for the last 2 years or so. I would say this has only been around for 2 years, and it's kind of at the intersection of the world of electrical engineering and also applied optics and also computational imaging in general, there's no good code base online, even like everybody's hacking their own stuff together. So we're planning on, with our upcoming ICCP paper, also publish a reference implementation of a lot of this for this end-to-end optimization for depth estimation. So hopefully that will help the community too. But yeah, sorry, that was
that sounds very good. I like your response and your perspective on this. I think this is a very, very important topic for the community across many applications.
Yeah.
The other question, I think maybe I'll just do one more in the interest of time to get to the audience. Yeah, so you were talking about, in the second part, you were talking about the power and a trade-off between power and quality of classification. And are you actually optimizing for the power consumption when you're training?
No. So in this case,
is that possible? Is there, can you mathematically characterize it in a loss function?
Ooh, that's a great question. I haven't really thought about this, but it may be possible. But in this case, we think about both the optics and the electronics as a fixed neural network. I think about it as one big neural network, and some of the neurons are implemented using digital computation, and some of the neurons are implemented using this free space optical propagation, basically. And typically in these feed-forward networks, at least, I would say, you kind of fix your network architecture and then you train it to get the optimal set of weights for each of the fixed neurons. There's no way for the algorithm to change what the network architecture is. So in this case, I would say the power savings come from the fact that you basically just pre-allocated half of the computation to the network and half of the computation to the optics. But I think if you think about other more adaptive techniques to neural network architecture optimization, for example, using reinforcement learning or other techniques that can actually change the architecture of the network, then I think we're talking about exactly what you're saying, is where we can do dynamic resource allocation to see, for a fixed power budget, what is the best performance I can get? What's the best architecture? And that's really a great question. And I mean, I haven't seen anybody looking at that, for example.
Mm-hmm.
Yeah, great question. So again, in this case, it's a pretty simple network. It's only 2 layers. Most real-world classification networks have tens or maybe 100 layers, right? So if you can only implement a single optical layer in optics, the savings are really dependent relative to the network size. And for a 2-layer network, the savings are pretty high. For a deeper network, the savings become marginal. So that's why this was more of a thought experiment, I would say. But it's great to see that, I mean, when people have looked at optical correlation and just doing optical convolutions for decades, this is not something new. I think what's really new here is this end-to-end design and the fact that we can actually implement multiple convolutions simultaneously, which is what actually a CNN layer does. I would say there's a lot of open challenges in this case. This idea of optical computing or doing optical AI is actually currently undergoing through a renaissance, I would say, in the world of optics and computational optics. A lot of people are working on this, all different aspects. And I think that's a really rich area for innovations also from the signal processing side. This is an interdisciplinary challenge where, photonics folks have to come together with folks that have the computational background to really make meaningful innovations. So if you have colleagues who work on optics, then it's probably worthwhile chatting with them a little bit.
Mm-hmm. Cool. I'll leave my questions there, and I wondered if anyone else, any of the other panelists have questions. If not, then let's go to the audience questions. And the first question is by Jiakai Liu, and their question is it possible to also make use of polarization?
Oh, well, first of all, hi, Jiakai. I hope you're doing well. Haven't seen you in a while, but it's good to hear that you're online. Polarization is interesting. I would say the models we're using for this end-to-end design do not necessarily account for polarization. We work with these scalar diffraction models that are actually polarization invariant, and that can be a problem. They just assume that the light is linear polarized and doesn't change the polarization. But you can definitely build models on the vectorial nature of light, for example, to use more sophisticated models of light propagation. If you want to optimize the optics, but then you're talking about, working with Maxwell's equations directly, and that becomes computationally pretty heavy, I would say. A good challenge moving forward, but a little bit challenging for the optics. I'd say there are a lot of cameras now that come with these polarization filters as a polarization filter array directly on the sensor. So that could be really interesting, where you have polarization encodes a lot of information in the scene, like surface normals, reflectance properties, material properties, and so on. It actually carries a lot of information. And thinking about optimizing a polarization filter array on the sensor could be a lot more feasible and interesting to extract more information from the scene. So I think polarization is an underutilized aspect or dimension of the plane optic function. And we haven't looked at it. The scalar diffraction models we've been using for optimizing optical elements don't apply for polarization, but I think there are ways of thinking about this that really make sense and that are computationally tractable. So this is a great direction for.
Yeah, thank you, Gordon. I'm really glad that my question triggers your thoughts about this study, but actually my question was about another study.
Okay.
You presented. Actually, it's the first study that you used, reflection from the light bounce on the wall and then get that information. So I was asking if you use different polarization directions of the laser, probably the surface property will lead to different reflection properties of the light and probably give you more information. Just wanna.
Oh yeah. That's great. So okay. Sorry, I misunderstood the question. So yes, you can do this non-line of sight imaging using different light modalities. What we're using is, lasers are generally polarized. We do not leverage the polarization in this case. We're only leveraging the time aspect here. So these time stamping capabilities. But we were part of a big DARPA project called Reveal, and there were many teams in there, and all the teams looked at different aspects and were successful in, extracting some kind of 3D-ness of this object using different modalities. For example, people looked at coherence properties and interference. People looked at light field properties that, give you some information. If the wall is perfectly Lambertian or diffuse, the light field on this side doesn't give you much information about the object here. But if you have a little bit of a specular highlight or some amount of glossiness, there may be some information there. And exactly as you said, you can potentially leverage polarization as well. If this wall here, the directly visible wall, preserves some amount of polarization somehow, I believe that should be possible. I would say Achuda Kadambi at UCLA has looked into a couple of different polarization-based imaging modalities. I forgot if he actually investigated this for non-line of sight imaging or not, but I think it's a great idea. Out of the top of my head, I can't come up with a paper that did this, but it should be possible depending on the reflectance information here on the wall and maybe the object too. Great idea.
Okay, thank you very much.
The next question is by Reza Fasal Rezai. They say, very interesting talk. Can you comment on the computational time required for the single photon imaging? Can it be done in real time?
Oh yeah, that's a great question. Yeah. So as I was saying, we've been mainly focusing on fast algorithms to do this. And I'd say both this light cone transform that we developed, which was a closed form solution for the inverse problem using a geometrics model, and also this wave-based solution, which we called FK migration. They both work in real time. And they're limited by a 3D Fourier transform. It ends up, in retrospect, both of these end up being a pretty simple processing scheme. You take the 3D data cube that you measure, which is the X, Y, and T. You do a 3D Fourier transform, and then for the LCT, we had a special transform that we developed in which inverse filtering, so element-wise division in the Fourier domain, became the closed form solution, followed by an inverse Fourier transform. In this wave-based solution, we actually take the the k-space, so the Fourier coefficients, and we have to interpolate them. So we have to resort the coefficients into different positions, then do an inverse 3D Fourier transform. So the techniques are slightly different, but in either case, it basically ends up being O(n) cubed log n, where n is the number of voxels in the data cube. And I mean, we were able to implement this in real time on a GPU, and we had a demo at SIGGRAPH and CVPR 2018 where we actually showed live, real-time reconstruction of certain types of hidden objects on a GPU. I'd say, so the computation can be efficient. I would say the big bottleneck is still the photon efficiency of these systems. You really get just a few photons back if you're thinking about Lambertian objects that are at reasonably longer range away from the imaging system. And even if you have a single photon sensitive detector, if you only have 3 photons coming back, you're going to have to do this many times. So I'd say the bottleneck right now is actually the acquisition time more so than the compute time.
Okay. Next question is by Huani Ju. And the question is, I would like to ask about coded image mentioned in deep optics. I'm impressed by the reconstruction from one photograph to a dynamic image. I'm curious, what signal does each program pixel record in this case, like photon histogram signal counted along with time?
Okay, let me see. So I think what you're referring to is
this one.
This one here, right? Is that right?
Yes, right,
okay.
Right.
So this work is actually inspired by a paper from Hajime Nagahara and Sri Nayar from ICCV, I believe 2013 or so. And they were the first to introduce this idea of taking a single image and then reconstructing a few frames from that. Back then, using compressive sensing, I'd say we replaced the idea of using compressive sensing with a neural network. And the big benefit of using neural network is that you can backpropagate into the optical codes. In this case, I think your question is more related to how we actually implemented this and what the degrees of freedom are. So people have prototyped these types of systems, these video compressive sensing systems, typically with the DMD that is kind of in front of the sensor and that has a very high modulation rate. In this case, we use a sensor that was made in the UK by Piotr Dudek's group in Manchester, and they actually fabricated a sensor that has some amount of compute directly on the sensor. So you can upload a little firmware program that has somewhat a couple of constraints, but you can basically program every pixel with its own exposure code. And, as I was saying, my postdoc Julian is an absolute wizard on programming this firmware and the hardware. And he got a loaner device from Piotr that he was able to program. And this is a fully integrated device, like it's doing all on the sensor. And I would say, if you're interested in the specific details of this sensor, which is called SCAMP 5, I would refer you to our ICCP 2020 paper. It's called Neural Sensors. And I would be more than happy to have a follow-up discussion if you have any specific questions after. And I can also connect you with my postdoc. Honestly, I haven't worked with this specific sensor. He implemented all of this, and I know that there are some constraints. I think you only have, you have a couple of analog registers with a few bits. It's not like you can program every bin at picosecond resolution. I think this camera has microsecond resolution with a few hundred bins within a reasonable exposure time. But there are some constraints on how you can actually program these bins because the register sizes are limited. And Julian came up with a really clever scheme of, uploading these registers onto the individual pixels and then basically on the fly translating this into an exposure code. So it's not super straightforward actually. But I'll refer you to the paper for more details and be happy to have a follow-up conversation with Julian as well.
Wow, thank you, Professor.
Okay. Next question is by David Morales. And the question is, those sign activation functions could be used in traditional neural network applications as classification. And what do you think would be the effect in the accuracy?
Yeah, this is a fantastic question. I think it's $1 million question, right? Like, is the sign something that can be broadly applicable to, other tasks? And the answer is maybe not really. So or maybe it's unknown. Feel free to try. So I'll tell you one thing. Like, we had the same idea, obviously, last year, and we looked a little bit at image classification also. In image classification, you use a CNN data set of images, training set, and you want to, learn some kind of classification error. The sign activation functions are really great at overfitting to a specific signal. So if you have one image, they have a great capacity of overfitting to this image. Signs are much better at that. ReLUs are not very good at overfitting. However, ReLUs are great at generalizing and interpolating between sparse data points. So when you think about training your algorithm on a training set and then evaluating on your test set, which has images that don't overlap, the ReLU is better at generalizing from the training set to the test set because it has better interpolation, extrapolation properties. It's kind of smooth, or it's not really smooth. It's actually piecewise linear. You can think about the whole network as, constructing hyperplanes. I mean, it's just a linear layer followed by a thresholding operator. So you have a bunch of hyperplanes that approximate your signal, right? In this case, we have something that, I mean, it's very difficult to interpret this. We have a nonlinear Fourier transform kind of a thing that has nonlinearities, and it's not really a Fourier transform because it has multiple layers, right? And it has these linear layers in between. But again, this is great at overfitting. In our initial experiments, we were able to get better results for classification, for example, on the test set, but worse results on the training set. Other way around. Better results at the training set, worse results on the test set, because these sirens are great at overfitting to specific signals, but they typically show oscillating behavior in between the data points. So for example, if you just have a really simple 1D function, right? Like maybe a polynomial, you have a few sampling points, you try to fit that 1D signal with the ReLU MLP, you get something that looks maybe piecewise planar or that looks pretty smooth. It's not that great, but overall the shape is great. Use a siren to fit that, you get perfect behavior in the data points, but you get oscillation in between. So I would say out of the box, it doesn't generalize well, but more recently we have been looking at, for example, using GANs to, in combination with siren, to learn a latent space in this space of sirens. And that works pretty well. I don't know if I can maybe show you just an image of that. So this paper was just accepted to CVPR, so you should see this coming up. So we have this paper called PyGAN. It's using sinusoidal activation functions to learn a latent space and generate 3D faces, 3D cats, cars, different types of 3D object. And the siren is really the backbone of this. So it is possible to use these architectures in the context of a GAN. And we recently explored this in this paper. Again, it's called PyGAN. I don't know how much you can get from me showing you this website, but the basic idea is to learn a latent space and generalize, and it works well. But it is a topic that's only just starting now. So this is pretty exciting. And I'd be, again, happy to chat offline. Certainly, this is one of the killer questions here.
Okay, thanks, Professor. Very interesting.
Okay, and I think we are continuing to get questions. So there are the next question is by Carlos. The question is, I have read some of your papers on deep optics and noticed that you use an L2 norm with the vision task loss. Which other loss function would you use to improve the optics? And also which loss function you would use if you need, for instance, to degrade the optics instead of improving it? Simply subtracting the L2 norm from the overall loss leads to an unbounded loss function.
Okay. I'm not sure if I fully understand this question, but let me just clarify one thing. We don't typically constrain the optics directly. The optics are learned end-to-end, supervised by a high-level loss function that depends on the task that you're optimizing. And as I was saying, we've looked at many different tasks. In some tasks, we want to do something like monocular depth estimation. Then the loss function is really an error between the estimated depth map and a ground truth depth map. And those loss functions could be L1, L2, something like that is common. We have looked at this image classification example in the context of this optical neural network. In that case, our loss function is actually a classification loss. We've looked at other applications, in which case, typically the easiest is to use some kind of L1, L2 loss. You could use a perceptual loss. The loss function is really defined by your application and what your goal is here. And that's the key idea, is that you can use a high-level loss function that penalizes something that may not be a per pixel loss, and backpropagate the error of this high-level loss function all the way into these low-level hardware parameters, like the height profile of the lens itself. And that is the key. So, what I was trying to convey to you is that this idea is very powerful. I'm not advocating for any one specific loss or any one specific application. I think this idea itself is more exciting, but typically you are looking at optimizing pretty large systems. So you want to keep it as lean as possible to optimize it on at least the few GPUs that we have on our cluster in an academic setting. We're kind of computer limited. If you work at Google, you have access to, unlimited TPUs. We don't have that. So to some extent, we work on a budget, on a GPU budget here. And I would say a lot of the design choices are typically made by the student being able to train their networks in a reasonable amount of time. So hopefully that kind of answers your question. But
Okay. We have one final question, and I'll just read this question. The diffractive optical element can be incorporated as a phase pattern on optoelectronic devices such as SLM. Any disadvantage compared to directly fabricating the optical element?
Oh, yeah. Okay. So, most people would not fabricate this diffractive optical element and then put it in here. It's very painful. Let's say, I wouldn't recommend it. As I showed you in this holography project, you can actually get a programmable phase SLM that can dynamically be reprogrammed, and you can put that in here. And that does, in theory, does the same thing. It's not as light efficient and so on, right? But in theory, it does the same thing. So if you're just getting started on this topic, I would recommend looking at that. The reason why we used a static fabricated mask is because what we wanted to show is that this power efficiency, right? So if we implement a single layer of the network in the computer, and we want to make the argument that the use of an optical CNN is to save power, then we can come with a spatial light modulator that requires more power to drive it than the power that it takes to implement the single CNN layer. So our design choice of fabricating this diffractive optical element was motivated by the fact that we really wanted to demonstrate that you can do it in a fixed optical element that requires no power. That being said, it is painful to learn the processes to fabricate these elements. It is expensive to use commercial services to make them for you. It's also expensive to buy an SLM, but an SLM you can use many times over, and a single phase mask only once, for one purpose at least. So I would say there are different, if you want to do prototyping, I think the SLM approach is better and easier. But if you want to demonstrate something that really requires no power, then you need a static DOE that's fabricated, and that was our goal for this specific project.
Okay, I think that's all the questions we have from the audience, and let me just ask again, if anyone has any more questions, feel free to chime in. Okay. Sally Wood says, great talk. So,
Thanks.
all right. Great. So thanks, Gordon, again for your wonderful talk.
Mhm.
And for the rest of the audience, the webinar series will continue in 2 weeks. So on March 23rd, our speaker would be Yonina Elder from the Weizmann Institute of Science in Israel. And so hope to see several of you 2 weeks from now.